All right, so let's get started here. We're going to continue our discussion of these electron configurations. Now introducing the idea of doing these electron configurations of ions. We've been talking about atoms up until this point. All right, so first we need an example here that we can work off of. So we're going to take a second and we're going to build the electron configuration for the fluorine atom. All right, so everybody take a second. Given where fluorine lives on our periodic table, give me its electron configuration. And once we have that, we're going to build one of those electron configuration diagrams so we can illustrate that electron configuration. So based on where fluorine lives on the periodic table, its last orbital in its electron configuration is the 2p5. And then we got to include everything that came before that, the 2s2, and before that, the 1s2. So here's our electron configuration for fluorine. And what we learned how to do last class was take that information and build one of these electron configuration diagrams. We're going to arrange these orbitals from lowest energy to highest energy. The lowest energy orbital is that 1s. Since it's an s orbital, it only gets one box. The next one up is the 2s, again an s orbital, so it only gets one box. And then finally our 2p orbital. Since it's a p orbital, it will get three boxes. All right, and then because we're going to fill in our diagram here with these arrows representing our electrons. Remember, we can fit a max of 2 of these electrons per box, and one of them is going to be what's called spin up, an upward pointing arrow. The other one's going to be what's called spin down, a downward pointing arrow. If we look at our 1s orbital, there's a total of 2 electrons, so it's completely full. So we'll put in 1, 2. Same thing with our 2s, completely full, 1, 2. When we get to our 2p orbital, we're going to have 5 electrons to add in there. But because these boxes are all at equal energy, we're going to fill it in this very specific way, where first we're going to go through and half fill all of these boxes, 1, 2, 3, and then if there's anything left over, we'll go back and start doubling them up. In this case, I got 2 more I got to put down for my total of 5. So that's 1, 2, 3, 4, 5. All right, so our electron configuration for fluorine, that 1s2, 2s2, 2p5, is illustrated on our electron configuration diagram here. All right, so this is what we learned how to do in the first 2 lectures of this week. And now we're talking about electron configurations of ions. So I'm no longer just interested in the electron configuration of fluorine, but what about the fluoride ion? All right, so first of all, based on the periodic table where fluorine lives, what charge is on that fluoride ion? -1. Cool. So I'm not talking about the fluorine atom anymore. I'm talking about the fluoride ion with its net charge of -1. All right, so if we look at this carefully here, remember our electron configuration tells us about all these electrons that are in that fluorine atom, right? That's what that 1s2, 2s2, 2p5 business is all about. It's telling us that 2 of fluorine's electrons live in this small spherically shaped orbital. 2 of fluorine's electrons live in a slightly larger spherical shaped orbital, and then 5 live in those peanut shaped orbitals, right? These are all the electrons in our fluorine atom. So when I'm talking about the fluoride ion, right, now I have a different number of electrons than the fluorine atom. In fact, did fluorine gain or lose electrons to become the fluoride ion? It gained an electron, right? Awesome. So we got to gain an electron. All right, if we're going to build the electron, electron configuration of this fluoride ion, it should have one extra electron in it, right? Because we got to gain an electron to make our fluoride ion. So let's look at our diagram here. Where might that one extra electron go? That 2p, right? Look, we got this missing space right here. We need to gain one electron in order to make our fluoride ions. So where is that electron going to go? Right here in that empty box. Okay, so the fluoride ion will gain an electron, and it's going to fill that 2p row. All right, so let's do this here for our electron configuration. That means it's 1s2, 2s2, and 2p6, right? We've now completely filled that p shell. All right, so if we look carefully at our periodic table here, the fluoride ion has the exact same electron configuration as which element, which neutral atom? Neon, right? A noble gas. So if we were to do our noble gas abbreviation, it would just be that of neon. All right? So why do all elements in that halogen column form ions with a +1 charge? Because they're all trying to fill their p shell so that they can adopt the same electron configuration as a noble gas. This is the same principle behind why these nonmetals form covalent bonds. They want to complete their octet, right? They want those full valence shells. Same idea here. They're trying to fill up those valence shells so that their electron configurations can be identical to that of a noble gas. All right, so electron configurations for ions. Importantly, as we just established, our anions, our negatively charged ions, they need to gain electrons. So then our positively charged ions, our cations, they're going to lose electrons. All right, so then let's just see, for an example, let's take a cation. Let's do the same thing that we just did. I want you all to give me the electron configuration for sodium. And then, given that electron configuration, I want you to tell me what the electron configuration for the sodium ion is. All right, so sodium being in that first column of the third row in our S block has the last electron configuration, or last orbital in its electron configuration of 3s1. Got to include what comes before that, the 2p6, before that the 2s2, and before that the 1s2. All right? So now in order for sodium to become the sodium ion, now I have to lose an electron. So I'm going to get rid of one of those electrons from my electron configuration. Which one do we think we're going to scrap? That 3s1. All right, so 1s2, 2s2, 2p6 will be our sodium's electron configuration. And which element shares that same electron configuration? Neon, again, one of our noble gases. All right, so what we're going to see is that our anions will gain electrons and our cations will lose electrons. And both are going to do so in order to adopt the electron configuration of the nearest noble gas. Remember, noble gases, they don't like to form bonds. They're all nice and stable all by themselves because they have these full valence shells. So why are cations losing electrons? Because they want to get to a noble gas configuration. Why are anions gaining electrons? Because they want to get to that nice, stable noble gas abbreviation, our noble gas electron configuration. All right, so in each of these cases here, if we take a metal, it's going to lose electrons in order to get to its nearest noble gas. An anion is going to gain electrons in order to get to its nearest noble gas. All right, so, oops. All right, let's just practice one more here. I want you to give me both the full and the noble gas abbreviated electron configuration for the sulfide ion. Which is the same as what? All right, so if I ask you for the noble gas abbreviation, that's like the easiest thing for an ion because it's just going to be that of the nearest noble gas, right? So sulfur, we're going to start here, but it's going to gain 2 electrons so that it adopts the same electron configuration as argon. All right, so these are always going to be the electron configuration of the nearest noble gas. That's why they're gaining electrons, or in the case of cations, losing electrons. So then if I need the full electron configuration for the sulfur ion, the sulfide ion, I'm going to give you that of the argon, right? That full electron configuration of the argon atom. So that's going to be a full 3p shell, 3p6, before that's 3s2, 2p6, before that's 2s2, and then finally in front of that is the 1s2. All right, so again, elements will either gain or lose electrons in order to get to the electron configuration of the nearest noble gas. That's why our nonmetals gain electrons, but our metals will lose electrons. All right, so In order to finish off our discussion of electrons and atoms, we're going to again take our example, our electron configuration diagram here. All right. And what we're going to do, actually we'll lay some groundwork here. What we're going to do is discuss what are called quantum numbers. All right, our quantum numbers are a way of specifying a particular electron in our electron configuration diagrams. All right. These are often called quantum number addresses. Because again, it's specifying the location of a specific element on our, the specific electron on our electron configuration diagram. All right, and we do so with these 3 digits. All right, so our quantum number address, 4 digits. Is composed of these 4 digits. N, L, M sub L, and M sub S. All right, so if I ask you for the quantum number address of an electron, you're going to give me 4 digits here. All right, let's talk about each one of these digits, what each one of these digits represent. All right, N is what's called our principal quantum number. Okay, and N is one that we've talked about before. The principal quantum number, this is what denotes the relative size of your orbital. Okay, so for example, in the 1s orbital, my principal quantum number N is simply equal to 1. That value that we put in front of that orbital shape. All right, what about in the 3p orbital? What is my principal quantum number? 3. Right? It's that value that's listed out front of your orbital, which corresponded to the row on our periodic table, right? And we talked about how this denotes the relative size of your orbital. A 1s orbital is smaller than a 2s orbital, is smaller than a 3s orbital, right? So that's our principal quantum number. That's going to be the first value in our quantum number address for our electron. All right. L is what's called the angular momentum quantum number. And if N is denoting the relative size of our orbitals, L is going to denote the shape of those orbitals. So up until now, we've been using a different sort of symbology for representing shape. How do we denote those spherical shaped orbitals differently from those peanut shaped orbitals? S and P and D and F, right? We have these letters that we use to denote those different shapes. Our angular momentum quantum number is going to be that exact same information, but just in numerical form. So an S orbital has an angular momentum quantum number of 0. A p orbital has an angular momentum quantum number of 1, d is 2, and what do we think F would be? 3. All right, and those are the only possible values for your angular momentum quantum number. Again, they denote the shape of the orbital. All right, so for our principal quantum number, if we think about what values are allowed for our principal quantum number, is there such thing as a 0s orbital? No, but we do have a 1, a 2, a 3, a 4. Our periodic table limits us to 7, but in theory, somewhere in the universe, there may be even larger elements. So our allowed values for n are just any counting number, any whole number greater than 0. So n can be 1, 2, 3, 4, etc., etc. Maybe somewhere in this universe there's an atom that has a principal quantum number of 25. I don't know. We definitely don't have one here on Earth. All right, but in theory, that principal quantum number can be any value greater than 1. When we look at our angular momentum quantum numbers and we talk about allowed values, again, we have these 3 shapes that we see here on Earth, these 3 types of orbitals that we see here on Earth. In theory, there could be an L value that's greater, all right? However, importantly though, when we start counting our p block, what's that first row in our p block? 2p. Is there any such thing as a 1p orbital? No. All right, so our value of L is limited by our value of n, okay? Our value of L can be anything from 0 all the way to n minus 1. All right, so just to illustrate here, we said that there was no such thing as a 1p orbital, right? A 1p orbital would be n equals to 1 and L is equal to 1. Well, that can't be. L has to be at most n minus 1, right? So the largest value that I can have for an n equal to 1 would be 0. All right, so then let's say if n is equal to 2, what is the largest allowed value for L? Right? L is allowed to take a maximum value of n minus 1. And if I take 2 minus 1, I get a value of 1. There's no such thing as a 2d orbital, right? I can only have a 2p orbital. And that's why my principal quantum number of 2 corresponds to that angular momentum quantum number of 1, right? That's the maximum allowed value. All right. Our next value, our next quantum number is m sub L, what's called the magnetic quantum number. All right, so strictly speaking, this corresponds to the orientation of your orbital. All right, and so what do I mean by that? Well, if we remember, we said that when we draw our electron configuration, we draw these three boxes for example, a p orbital. All right, we got these three boxes. What do those boxes correspond to? Well, remember when we were discussing our p orbital, we were talking about how it's got this peanut shape, but there are actually three peanuts. Hold on, let me find this picture. And the difference between them is just how they're oriented in space. One of those peanuts is oriented up and down, the other one left to right, and the other one front to back, right? So they're all these peanut-shaped orbitals, but they're just oriented differently in space. So our magnetic quantum number is going to correspond to which of these three we're talking about here, all right? Practically speaking, what it's going to correspond to, let's actually just take a look at that electron configuration diagram again. Let me grab this example. All right, what it's going to correspond to practically is we're going to number our boxes in our orbital diagrams, in our electron configuration diagrams. All right, so let's take this electron configuration that we built for fluorine. We'll just do the fluorine atom. Okay, so first of all, before we talk about our angular momentum, or before we talk about our magnetic quantum number, for each of these three orbitals here, everybody take a second and give me the value of n and the value of L for each of these three orbitals, based on what we discussed about n and L. All right, so remember our principal quantum number n denotes the relative size of these orbitals, that number that's listed out front there. So for a 1s orbital, that principal quantum number is 1. For a 2s orbital, that principal quantum number is 2. And for a 2p orbital, that principal quantum number is 2. The angular momentum quantum number, the L, corresponds to the shape of that orbital. So a 1s orbital is S, has an angular momentum quantum number of 0. A 2s orbital, also that spherical shape, has an angular momentum quantum number of 0. And a 2p orbital, P, has an angular momentum number of 1, right? Remember, the shape of that orbital uniquely corresponds to that value of L. S, P, D, F. That's what you got to remember is the order of those. All right, cool. So we see that those first two numbers specify what level we're on here, right? So what our magnetic quantum number is going to do is point to what specific box we're talking about. What are our allowed values for the angular for the magnetic quantum number? All right, your magnetic quantum number can take on a value from negative L all the way to positive L. All right, so what we're going to do is we're going to annotate fluorine's electron configuration diagram here with these M sub L values. I'm going to write them in purple to keep them distinguished. Each box is going to get an M sub L value here. All right, and again, M sub L can take on a value from negative L all the way to positive L. So for this 1s orbital, my value of L is 0. What's going to be the magnetic quantum number of this box here? 0, right? Takes on a value from negative L to positive L. If L is 0, negative 0, positive 0, same number, right? So this box here gets the the magnetic quantum number of 0. All right, what about my 2s orbital? What's the magnetic quantum number? Also 0, because it's still an s orbital with that L value of 0. All right, but now let's look at our 2p. What are our allowed values for our magnetic quantum number of the 2p orbital? So it's from negative L to L. If L equals 1, that means that our M sub L can be negative 1, 0, or 1. And that's exactly how we're going to label our boxes, from negative L to positive L. So this very first box in my 2p, that's the -1 magnetic quantum number. My next box is in the middle here, the 0. And that last box gets that magnetic quantum number of 1. All right, we take on a value from negative L to L. We're just listing those in order when we're labeling our boxes. All right, so our principal quantum number and our angular momentum quantum number, they're going to specify a particular row in our electron configuration, right? N equals 2 and L equals 1 means I'm talking about this row right here. That magnetic quantum number then points to a specific box on that diagram, right? So if I tell you that my principal quantum number is 2, my angular momentum quantum number is 1, and my magnetic quantum number is 1, that means I'm specifically referring to this box right here. All right, so then the last step, we need one more digit to specify a particular electron in that box, and that's going to be what's called the spin quantum number. We represent that as M sub S. And we talked about this concept of spin last class. Electrons can adopt one of two spins, and what did we call them? Up or down, right? The arrow pointing up, that'd be a spin up electron. The arrow pointing down would be a spin down electron. So now we're going to translate that same information, but using a numerical value here. A spin up electron gets a spin quantum number of +1/2. And a spin down electron gets a spin quantum number of -1/2. And those are the only two allowed values for your spin quantum number. So why is it a half? Like, where the hell did that come from, right? Where did any of these quantum numbers come from? What psycho made up this whole system here? Well, remember, this whole theory of electrons and atoms relates back to that big, ugly math problem that we weren't even going to touch, right? We said that this entire theory is built on, let me find it real quick. This big, ugly math problem here, right? And we don't know this math. We're just going to look at it and be like, okay, yay, math, great. It's cool, somebody did this. All right, so where do those numbers come from? Those turn out to all be variables in this big, ugly math equation here. Some psycho went and solved that big ugly math equation. And what fell out are these 4 quantum number variables. You can see your principal quantum number, your angular momentum quantum number, your spin and your magnetic quantum number are buried in here somewhere. These were solutions to this big ugly math problem here. And they point to specific electrons. And again, we're not going to do the math. We're trying to qualitatively understand this business. Right? But why is it plus 1/2 instead of just plus 1? Because that's what the big ugly math equation tells us. AKA, we're just going to trust that somebody smarter than us laid this all out, and we're going to say, okay, great, sounds good. All right, so if I'm going to go back to my diagram here, again, our whole goal is to specify a particular electron in this diagram. All right? So I want you to tell me the 4 digits in our quantum number address that correspond to this electron right here. What 4 digits do I need to specify this guy? Again, we're going to need a principal quantum number, an angular momentum quantum number, a magnetic quantum number, and a spin quantum number. If I got 4 of those, I uniquely point to 1 electron on this diagram.
Is positive 1/2 the left one? The left
Spin up, the arrow pointing up is the plus 1/2, the arrow pointing down is the minus 1/2. Yep. All right, so we kind of laid out a good bit of cheat sheet information here. We've established that our principal quantum number at this location is 2. Our angular momentum quantum number, because this is a p orbital, would be 1. My box where this electron is located, my magnetic quantum number, would be 0. And lastly, my spin quantum number for this arrow that's pointed down would be -1/2. All right, so again, those 4 digits specify a specific electron on my electron configuration diagram here. They're the address of that electron. All right, so I'm going to get rid of our cheat sheet information here, and we're going to do a few more examples. Okay, so first of all, I want everybody to tell me the address, the quantum number address of this very first electron in our electron configuration diagram. What are the 4 digits that specify that electron? once you've got that done, you're going to then do kind of the reverse. I'm going to give you the quantum number address of an electron. I want you to locate it on our diagram here. Right? 2, 1, -1, -1/2. What the heck am I talking about there? Where is that electron located on that electron configuration diagram? All right, so first things first, our quantum number address here. All right, these first two, my first two digits in my quantum number address are going to be reflective of this information here, this 1s orbital. So my principal quantum number is 1. My angular momentum quantum number is unique to that s orbital. S is 0. All right. My magnetic quantum number is then going to specify this particular box that I have on my electron configuration diagram. And there's only one of them here. All right. But be careful. Remember that the values of this m sub L, the next quantum number, can be from -L to +L. And my value of L here is 0. So when you have just this one box, it's not 1. That one box's quantum number address is 0. So this first electron here would be 1, 0, 0, and then have a spin of +1/2. Awesome. All right, so now I'm going to find a particular electron given its quantum number address. All right, these first two pieces of information here tell me which one of these levels I'm going to look at. This tells me that my principal quantum number is 2. And if my angular momentum quantum number is 1, that corresponds to what shape? P. So I know that I've got an electron somewhere in here. Right? The next one corresponds to the box that these electrons live in. And remember, these can take on a value from -L to +L. So I'm going to list them, -1, 0, 1. So now I know I'm talking about this very first box here. All right, and if I'm talking about my -1/2 electron, I'm specifically referring to this spin down electron here. All right, so this quantum number address corresponds to this specific electron. All right, so if I point to an electron, you should be able to tell me its address. If I give you an address, you should be able to point to an electron. All right, and then lastly, just to tie this in here with what we did at the very beginning, let's ask fluorine gains an electron to become the fluoride ion. What is the quantum number address of that electron? All right, so remember we looked at this diagram here and we were like, we need to fill this in with one more electron. Where's that electron going to go? In that missing spot right here. So now we just got to identify the quantum number address of this electron. If it's a 2p electron, that means its principal quantum number is 2, and its angular momentum quantum number is 1. My magnetic quantum number is going to correspond to this specific box here. And we label these -1, 0, 1. So this box here would be the magnetic quantum number of 1. And lastly, what's the spin of this electron? -1/2, right? A spin down electron. So that's the unique quantum number address of that electron. Cool. Did you do this stuff last semester? Quantum numbers? Okay. Okay. Yeah, I wasn't sure how. Okay. Okay. The video, you mean? Yeah, okay. Yeah, you're fine. You're fine. It's not too bad when you get the hang of it.
Okay, yeah. Because I remember like when we have to memorize that, but then I don't think we have to like label all the spin down and spin up.
Okay, all right. Yeah, that's just the last one to specify a particular electron.
Okay, yeah.
Yep.
If you have a chance to review my test.
I got it, but I haven't looked at it yet. Your scores will be posted later today.
You say you're gonna move over and see if I could finish the.
Right, yeah. Everything will be posted later today, so I'll let you know.
Thank you. For the spin quantum number,
Uh-huh.
the MS, if you have like a 3s box or energy, what would the MS be?
They're all always going to be +1/2 or -1/2 for electrons. Those are the only two possible spin values. Other particles have other spin values, but for electrons, which is the only thing we're talking about, it's either +1/2 or -1/2.
And the magnetic would be.
So the magnetic, if you're talking about, what did you say, 3p, is still going to be limited by the p's, so the -1 to +1. If you're talking about a d orbital, all of a sudden it can be from -2 to +2, or an f would be -3 to +3. So it's going to depend on that, the shape of that orbital.
Okay, thanks.
I have a question for last week's assignment. So I did everything on time. I just forgot to.
Yeah, that's fine. Send me an email.
Okay.
I can see what date you did it, and if you did it on time, I'll erase the late penalty.
Thank you very much.
Yep.